These notes go as section 3.3 in your packet, and this is about how to solve equations when we have variables on both sides of the equal sign. Let's start out with a balanced scale model to help us picture what it looks like when we have variables on both sides of an equation. So the picture that's shown here, the balanced scale model shown here, has x's on both sides of the equal sign. On the left-hand side, we have 2x's plus 1, and on the right-hand side, we have 1x plus 3 more. So shown here is the equation that matches this balanced scale model. 2x's plus 1 equals, or balances out with, a single x plus 3. So if we were to take a look just at the balanced scale model, what might we do first? Remember that we're trying to get our balanced scale model so that it has a single x on one side and some number of ones on the other side so that we can tell what a single x is equal to or balances out with. And there's a number of different steps that we could take. One thing I noticed is that there are x's on both sides. And so I could take away an x from the left-hand side and an x from the right-hand side, and my equation would still balance. If I did that, I'd be left with a single x on the left and still that 1. Now there would be no more x's on the right-hand side. All I would have is 3. I can see that this got me a step closer to my goal of having just x on one side and some numbers on the other side, because now I have the and some numbers on the other side part. By taking an x away from both sides of the equation, I made it so that what was left had x's only on one side. What does this look like when we're doing the math on paper? Well, we subtracted an x from the left-hand side, and we subtracted an x from the right-hand side and an x from the left-hand side. We had 2 x's before. We took one of those x's away, so we're left with a single x. Still, plus 1, because we didn't change that, equals or balances out. Well, we had an x and we took away an x, so there's no more x's. All that's left is positive 3. So now we have x plus 1 equals 3, and that matches our balanced scale model. Now we can take 1 off of both sides of our balanced scale. Why are we doing that? Well, that gets us to have only x on this side of the balanced scale, and on the right-hand side we're left with 2 blocks. So now I know that a single x is equal to 2 1s. What does that look like when I do the algebra? Well, I subtract 1 from the left-hand side, and to keep my equation balanced, I subtract 1 from the right-hand side, and I'm left with x equals 2. So you see the steps that we take when we're solving for x, when we're getting x all by itself on one side of our balanced scale, are really no different whether we start with all the x's on one side or we start with x's on both sides. All we're doing is taking steps that keep our equation balanced until we get a single x on one side and some number that it balances on the other side. Now, let's start your notes in your packet. Here's an equation. 5n minus 7 equals 9n plus 21. And we want to solve this equation. We want to find out what single number for n makes this equation true. This equation is sometimes true, and whether or not it's true depends on the number we plug in for n. And we want to find that number for n. So here's our original equation. The first thing that we're going to do is we're going to try and gather up all of our n's on one side of the equation. You could subtract 9n from both sides. That would be fine. That would get rid of the n's on this side. What I notice is then 5n minus 9n, that's going to leave me negative 4n on this side. And I'm not such a fan of negative numbers if I don't have to use them. So instead, what I'm going to do is I'm going to subtract 5n from both sides. Why 5n? Well, that's going to get rid of the n's on this side. When I do that, 5n minus 5n is 0, and 0 minus 7 is negative 7. On the other side, 9n minus 5n gives me 4n, and I still have plus 21. Okay, so I've got it so that I have all my n's on one side. Now I'd like to get it so that I have all of my numbers on the other side. So in this case, I'm going to have to subtract 21 from each side. I'll take 21 away from the right-hand side. That's going to leave me just the 4n over here. And to keep my equation balanced, I have to subtract 21 from the left-hand side. Positive 21 and negative 21 add up to 0. 4n plus 0 is just 4n. Negative 7 minus 21, it might help you to think of that as plus negative 21. Negative 7 plus negative 21 gives me negative 28. All right, so I've got my n's on one side and my constants on the other, but I still have this 4 in front of the n. So what I need to do is take that expression, 4n, and divide it by 4. And to keep my equation balanced, I have to divide the left-hand side by 4 as well. 4 over 4 is just 1, so on the right-hand side I'm left with plain old n, 1n. And negative 28 over 4, well, 28 over 4 is 7, and a negative divided by a positive is a negative. So the solution, the one number for n that makes the original equation true, is n equals negative 7. Now let's look down below. Now it tells us right in the example, an equation with no solution. You worked with some of these equations earlier. These are the equations that were never true. Now you might look at this equation here and it's not immediately obvious that there's no solution to it. That's fine. We'll be able to tell that there's no solution once we start working. So what do we think we might do first to solve this equation? Well, I noticed that I have a number on the outside of the parentheses, so maybe I'll go ahead and apply the distributive property first. 3 times 2x gives me 6x. 3 times 1 gives me 3. So I end up with 6x plus 3 equals 6x. This statement is never true. How can we tell that it's never true? Well, it's never true because the number 6x is never 3 more than itself. This equation says that 6x is equal to 6x plus 3, that 6x is 3 more than itself, and that just can't be true. So this equation has no solution. There is no number you can plug in for x that makes this equation balance. Now let's say that we didn't realize that up here. We have 6x plus 3 equals 6x. Let's say that we're trying to get the x's by themselves. Let's say that we subtracted 6x from this side. I'll take 6x away from here, and to keep my equation balanced, I'm going to subtract 6x from there. Okay, so we're subtracting 6x from each side. Well, 6x plus negative 6x is 0. 0 plus 3 is 3. And then on this side, we have 6x minus 6x. That's 0. 3 equals 0. That statement is never true. 3 is never equal to 0. No matter what you do, 3 isn't 0. What that means, notice that there's no x's in that equation. What that means is that no matter what you plug in for x, the equation that you started with is always going to simplify to something that's false, no matter what x is, because there is no x in this. That means that the equation has no solution. When you work through a problem and you get an answer like this, a statement that is false, that tells you that there's no solution to your original equation. Next, we're going to look at solving an equation that is always true. You worked with some of these before, and you noticed that some equations work no matter what you plug in for x. Let's see what one of these equations looks like when we start to work with it. So we have this equation, 4 times x plus 2 equals 4x plus 8. So the first thing that we might do in this is apply the distributive property. 4 times x is 4x plus 4 times 2 is 8. So we get 4x plus 8 equals 4x plus 8. Okay, that's the exact same expression on both sides of that equal sign. So this statement, 4x plus 8 equals 4x plus 8, is true. It's always true. It's always true. The equation has infinitely many solutions. No matter what you plug in for x, this equation works. You could plug in 0 for x and it works. You could plug in 100 for x and it works. You could plug in pi for x and it works. Let's say that you're sort of chugging along in your math and you don't realize that the two sides of your equation are already equal. Let's see what the math would look like if we started with this equation here. We had 4x plus 8 equals 4x plus 8. So if I'm trying to get all of my x's together on one side of the equation, maybe I look and notice there's a 4x here, and so I'm going to subtract 4x from this side, and to keep my equation balanced, I subtract 4x from this side. When I do that, I end up with 4x minus 4x is 0, plus 8 is 8. On the other side, 4x minus 4x is 0, plus 8 is 8. I end up with this equation, 8 equals 8. That's always true. And notice there's no x in this. So no matter what x is, this equation is always going to be true. Next, I'd like you to please pause this presentation while you work through the 4 checkpoint problems. You will be checking the correctness of your answers while we're together in class. Last, we're going to take a look at solving a word problem that uses an equation that has variables on both sides. So the problem says, find the perimeter. Remember, perimeter means the distance all the way around the square. So if I start in one corner and I walk all the way along one side, then along the next side, then along the next, and then along the next side, if I walk all the way around that, how far will I have walked? What is the perimeter, the distance around the outside edge of that square? And it matters here that it tells us that this is a square. It gives us some dimensions, 3x and x plus 6. We know something about a square, and we know that in a square, all of the sides have equal length. So this expression, 3x, that tells you how long this side is, must be equal to x plus 6, the expression that tells you how long this side is. Because these two sides, these two lengths, have to be equal to each other, because the sides of a square are all the same length. So now we have this equation, 3x equals x plus 6. So I notice that I have x's on both sides of my equation, so I'm going to take x away from both sides. I have 3x on the left, and I'm going to subtract an x from that. I have x plus 6, and I'm going to subtract an x from that. Now notice that in this problem, we're working through this where we're showing our subtracting x from both sides horizontally. We're showing it on the same line as our original problem. Oftentimes, you write the subtraction underneath the x, and that's fine. It's just two different ways of formatting a subtraction problem. So if it's easier for you in a situation like this to write it as 3x minus x here, minus x here, that's fine. We're just formatting. It's like back in elementary school. Sometimes you did your subtraction problems like this, and sometimes you did them like this. They were the same subtraction problem, we're just arranging it differently. All right, so I had 3 x's and I took away an x. That leaves me with 2 x's on this side. I had an x and 6 more on this side, and I took away the x, so all that leaves me is the 6 on this side. So I have 2x equals 6. To get the x by itself, I'm going to divide both sides by 2. 2 over 2 is just 1, so 1x is plain old x. And 6 divided by 2 is 3. So x equals 3. Well, that's all well and good, but the problem didn't ask me what x is equal to. The problem asked me the perimeter of the square. So we still need to use x to find the perimeter. So we're going to plug this number we found for x. X has to be 3 in order for these two sides to be equal to each other. We're going to plug that in to either expression for the length of the side of a square. So I could plug 3 in for x here, 3 times 3 is 9, or I could plug 3 in for x here, 3 plus 6 is 9. Either way, it tells me that one side of the square is 9 units long. So let's say I plugged into the 3x side, and I said that x had to be 3, so I'm going to take this x and replace it with a 3. 3 times 3 is 9. The perimeter is the distance all the way around the square, and so we have 4 sides that are of an equal length, so we can take the length of one side and multiply it by 4. So 9 times 4 is 36. So the perimeter of the square, the distance all the way around, is 36 units. Last, I'd like you to go ahead and work through a similar process to find the perimeter of the square that's shown here. If you're feeling stumped and you're not sure what to do, look at the example problem right up above. This is the end of the notes for section 3.3.